Okay, pre-cal 12, here we go. We're up to video 19. We are graphing rational functions. So we did the work on understanding vertical asymptotes and horizontal asymptotes, y-intercepts, x-intercepts, all that stuff. We are now going to put it all into to effect, and we are going to graph these things. Now, funnily enough, a kid today said, you know what, Mr. Hurlar, you're really not as energetic and upbeat as you are in your YouTube videos as you are in class. I was like, you know what, you're right. But I guess if I was, then you wouldn't even bother coming to class. You see, you come to class to see the show. So maybe it's a little dry here. I'm also sitting in a room by myself. So it's a little bit harder to be super energetic alone. It's kind of strange. Try it. Okay, so here we go. I will do my best. But this is what we talked about last time. When you're graphing a rational function, you always want to start with identifying your vertical asymptotes. Now, you can't do your holes until you factor, but vertical asymptotes oftentimes stare you in the face. You want to consider your horizontal asymptotes, then your holes, then your intercepts, and then you make a table of values to find your general peak and valley points. So let's go. Graph this rational function. Well, what's my vertical asymptote? Well, what is my denominator not allowed to be? It's not allowed to be 0. When does that occur? That occurs when x is equal to 1. So boom, I have a vertical asymptote at x equals 1. So I'm going to draw that in first. So I know my graph will not go anywhere near, well, it'll go very near, but it will not touch that line. Okay, now let's find our x-intercepts. X-intercepts occur when y equals 0, or g of x is 0. But just look at this function. Is that even possible? The only time that's ever going to happen is when the top is 0. And in this case, the numerator is never going to be 0, so this is not possible. So there's no x-intercept. Okay, well, what about my y-intercept? My y-intercept occurs when x is 0. So I have 1 over 0 minus 1, which gives me 1 over negative 1, which gives me, oh, lovely, negative 1. So I have a point for my line. I have my y-intercept at 0, comma, negative 1. Boom. It's the only point I know is on my graph right now. So there's x-intercepts done, y-intercepts done, vertical asymptotes done. There's no holes on this one, so let's just try horizontal asymptotes. So remember, for horizontal asymptotes, you divide every term by the highest degree power in the denominator, which in this case is just x. So I have 1 over x over x over x minus 1 over x, and we are concerned when x is going to infinity, so getting increasingly large. So what do I get here? I get 0 on top, and then 1 minus 0 on the bottom, so 0 over 1, so my horizontal asymptote occurs at 0, which means I have a horizontal asymptote right here. So I've done all that. So now I just want to check the behavior of my graph. As I get infinitely close to my vertical asymptote from either direction, but then also as I get infinitely away from my x to see what the behavior is at my horizontal asymptote. So for this, it can be handy to draw a table of values. When you get better at this, you get really good at getting key points and then predicting general behavior. So let's just see what happens. Considering I have a point at 0, comma, negative 1, let's start getting closer and closer to 1. So how do we get closer and closer to 1? Well, 0.9 is pretty close to 1. Now, when that happens, I just want you to, I'm not going to do this for every single one, but you have 1 over 0.9 minus 1. And now what that's going to give you is that's going to give you a negative number in your denominator, but a small negative number. So 1 over negative 0.1, which actually gives you negative 10. Now you can imagine, as this number gets closer and closer and closer to 1, so if it was 0.99999, so if you did that, 5 nines minus 1, then this number becomes 0.00001, which means this number just gets bigger and bigger and bigger. So that means that our graph, as it gets closer and closer to that asymptote, is going to shoot down towards negative infinity. So there's the behavior of the line going that direction. Now, what about then as I go the other direction away from the vertical asymptote? So what if I'm heading into the negative x realm? So if x becomes, let's just say, negative 10. Well, now I'm going to have 1 over negative 10 minus 1, which is 1 over negative 11. And then if x was negative 20, well, then I would have 1 over negative 21. So my number is getting smaller and smaller and smaller from the negative towards 0 on my y value. So it's going to go like this, and it's going to get infinitely close to my horizontal asymptote, but it isn't going to touch it. So that's the behavior on that side. Thing is, you're not done because you have to test the behavior on the other side of the vertical asymptote as well. So let's try right after my asymptote. So when x is 2. So when x is 2, you have 1 over 2 minus 1, which is 1 over 1. Okay, so that means I have another point right here. So you can kind of maybe infer that the behavior is going to be very similar. Because if we get infinitely close now to 1 from what we say the right, and the notation on that would be 1 plus, so we're getting infinitely close to 1 from the positive side of it, and I don't mean positive, I just mean 1.00001. Imagine what that means. We have 1 over, I'll just use an extreme example, 1.0000001, right? We're getting very, very, very close to 1. And then minus 1. So again, we're going to have 1 divided by a very, 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 very small number, which is going to give us a very, 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 very big number. So obviously, this point is going to shoot up. And as our x value increases infinitely, we're going to end up with a very, very, very small number on the bottom, because let's just say x was 10. We now have 1 over 9, right? And did I end up using the table of values here? No, but you can. But I did this more step by step, piece by piece. But if you can get the general behavior, it's not going to change, because we know that our line is, we know that our line is going to approach that asymptote, because it's a horizontal asymptote, as x gets infinitely larger. So that is going to be the general behavior of our first rational function. All right, so let's look at another one. Now, in order to save you a bit of time with respect to crunching the numbers of behavior, it's in your notes, so you can look at the table of values from there, and I'll just sort of explain it as best I can as I go. But here, we're definitely going to start with horizontal asymptotes, vertical asymptotes. So vertical asymptotes occur when our denominator is 0, and in this case, we have a difference of squares. X squared minus 1 factors to x plus 1 and x minus 1. So that means at x equals negative 1 and at x equals positive 1, we have potential vertical asymptotes. Now I said potential because our numerator is going to be factorable. So let's actually factor a numerator, and we get x minus 6, x plus 1. So actually, our whole function looks like this. And we're going to have one of our factors cancel out. So what we know at least for sure is that this one, when x equals 1, is still going to be a vertical asymptote. But what that canceling out has done is it's now going to create a hole. So for our hole, so this was our only vertical asymptote, because this is going to become the x value of our hole. We take that given x value and we plug it into our remaining simplified function. If you don't remember this, rewatch the previous video. So we end up with negative 1 minus 6 over negative 1 minus 1, which gives us negative 7 over negative 2, which gives us 7 over 2. So it means we have a hole at negative 1 comma 7 over 2, which is 3.5. So that means on our graph in green, at x equals negative 1, up 1, 2, 3.5, we're going to have a hole right there. So we know that. Okay, so we've done our vertical asymptotes, and due to the fact that we had a canceling factor here, we have a hole. So those are done and on there. Next step. Next step is going to be to do our horizontal asymptote. Now, rather than do all the XX simplification, you might be looking at this and saying, okay, I have the same degree terms top and bottom. And when I have the same degree terms, my horizontal asymptote is the ratio of the leading terms. You might remember that. So in this case, it's 1 over 1. So we have a horizontal asymptote at 1. So let's get that in there. So great. Now we're looking pretty good. In the notes, I've done that whole x squared over x squared minus 5x over x squared. So please have a look if you want to get that rather than just the remembering piece of your horizontal asymptotes. So now next up is our y-intercept and our x-intercept. And since in this example, since our horizontal asymptote is not on our x-axis, we're probably going to have an x-intercept. We don't guarantee to have one because our graph could exist only in the upper two quadrants, but we very well may. And remember that for our x-intercepts, it's when y equals 0. So if y equals 0, we only need to prove when our numerator equals 0, because that will make the entire fraction 0. So when does that equal 0? Well, that equals 0 at x minus 6 and x plus 1, which meant when x equals 6 and when x equals negative 1. Now we know we're going to disregard one of them, right? We're going to disregard this one because this one was a hole in our graph. So that's not an x-intercept, but that one is. So we're going to have an x-intercept at 6, 0, right there. The only other one we want to consider now is our y-intercept, and our y-intercept occurs when x equals 0. So in this case, we will set x equal to 0, and we'll end up with y equals 0 squared minus 5 times 0 minus 6, all over 0 squared minus 1, which is negative 6 over negative 1, which is 6. So our y-intercept is here. Now, even just from this information, you can probably almost determine what your graph's going to look like. So like I said, the table of values are going to be provided to you, but just consider the simplified function that we had, right? We had x minus 6 left, and we had x minus 1 left. Right? So pick values for x if you want to here, and you can kick out values of y, and what you'll get is you'll get points on your grid. So let's just take x equal to negative 5, because then it'll be like, where do we exist along here, right? So if we take x equal to negative 5, we end up with negative 11 over negative 6, which is 11 over 6, which is almost 2. So we're going to be just below 2, so there. Bear in mind, you might think, wait, that's only 1. Nope, because we're looking from the x-axis still, not from our asymptote. But you can gauge then that this line is going to be coming down. It's going to produce a hole there, and it's going to continue, and then it's going to approach our horizontal asymptote. And since we know we have an x-intercept at 6, 0, then that thing has to go up towards our asymptote as well. And it means that this line is going to come around and down because it's not going to touch our vertical asymptote either. And again, I've crunched a few numbers there to show you where those values occur, but that is going to be the general behavior of that function. All right. So let's look at another one. Now for this one, you're going to see some interesting behavior, okay? So first, vertical asymptote. What's the bottom? The bottom factors to x minus 1, x minus 1. So in this case, since we have the same factor on the bottom, we only have one vertical asymptote, and it occurs at x equals 1. There's no way we're going to get a canceled factor here, so we don't worry about holes. We just have the one vertical asymptote right there. Now for this next one, for this one, for the horizontal asymptote, let's look at, we're going to divide everything by the highest degree power in the denominator. So in this case, x squared. And remember that we do some x canceling here. So both the x squareds are going to cancel with 2 there. That's going to give us a 1. That's going to cancel with one of those. So in this case, you're going to have x over 1 minus 2 over x plus 1 over x. And we're talking about when x goes to infinity. And herein lies an issue, because on the bottom, we have the number 1. That's going to be a 0 and a 0. But on the top, we still have an x left, which means we are not converging. So we have no horizontal asymptote here. Okay, no horizontal asymptote. So we have no horizontal asymptote, and we have no holes. So all we have is the one vertical asymptote. Now, we can still find x-intercepts and y-intercepts, and in this case, I don't want to say it should be intuitively simple for you, but just look at the numerator. Because when do we have, when x equals 0, right, we have our y-intercept. But when x is 0, this whole thing's 0. So that means we have an intercept at the origin. And since that's our only factor on the top, that can be our only x-intercept as well. So we only have that one point. And now from here, we just need to consider the behavior on both sides of our vertical asymptote. We don't have a horizontal asymptote, so our line isn't going to look towards anything. So in this case, our table of values will actually make a little bit more meaning, because we can't just estimate at a certain point, because it might do some funky bending or moving. And I'm just going to write these numbers down because I've crunched these in your notes already. But what I did was I tested some points as I got closer and closer to my vertical asymptote. So when x was 0.9, so as I got really close from this side, right, as I approached from here, my y value spat out already at 72.9. So this thing is going to shoot up incredibly fast. And it's going to shoot up like that for good. But then what about as I moved away? So when x was negative 10, so my x value is now moving away, I was only down at negative 8.26. So when I'm at negative 10, I'm only down about here. So this graph is going to kind of slowly meander its way down. And then when we got to negative 1,000, so as we're well along our x-axis into the negatives, we eventually got to almost negative 1,000 on our y. So you can see it's almost becoming a linear line on a diagonal there. It's almost a 1-for-1 drop, but it isn't. So it's going to have a slight bend to it. But okay, what about the other half? What about the other side of my asymptote? So the first number that I took directly after my asymptote. So, well, not directly, but close enough to directly, 1.1. And from that y value, you plug that into your equation, you get a y value that spits out at 133.1. So again, this thing is now going to come down from here quite quickly. And do we have an exact intersection point? We can't say with any certainty without testing points. So what you could do is you could try to test x equals 2. Because why not, right? It's the next nice graphical intersection after our vertical asymptote. And if we do that, what do we get? Well, we get 8 on top. We get 4 minus 4 plus 1 on the bottom. So we actually get a decent value here, right? We get 8. So before I draw my line any further down, let's get that back in there. I actually have a point here. Now on your graph, on your notes, I've changed the scale. So you can see we still cross at 8, but we cross a little bit lower than we did. So this thing is going to come down. And then what happens after 2? So then if you start testing some points, you want to kind of see if you go a little bit lower. And it turns out that we don't go much lower than 8. What happens is we dip down, and then this thing shoots right back up. So when x is 10, so as you move outwards when x is 10, you're already back up at 12. And then when x gets to 1,000, you're at 1,002. So you almost again get into a linear line going that direction. So that's a really funky graph, right? Doesn't look like anything we've seen yet, but that's what happens. These aren't necessarily all going to be cookie cutter. This is a different look at a rational function. Okay, but we got one more to look at. So here we go. Let's do a little list here. We want horizontal asymptotes. We want vertical asymptotes. We want potential holes. We're going to want x-intercepts. We're going to want y-intercepts. And then we'll go from there. So horizontal asymptotes, I'll let you either look at the x squared, right? If we're taking the highest degree power on the bottom and writing every number over it, I'll let you have a look at that in the notes and how that works through. But remember, the power of the denominator function is larger than the power of the numerator function, which means that our horizontal asymptote is going to be our x-axis. Now, again, I don't expect you to remember that stuff, so knowing how to do that process that we showed earlier and is shown in the notes is helpful. Now, what about vertical? So horizontal asymptote, yes, at y equals 0, which is the x-axis. So what about vertical asymptotes? Well, let's factor the bottom. We factor the bottom and we get x minus 2, x plus 1. So we're going to get vertical asymptotes at x equals 2 and x equals negative 1. And neither of those are going to cancel because there's no factor that matches that in our numerator, so there's no holes. Those are both going to be true to form vertical asymptotes. Now, before I continue and actually graph this function, there's a note I want to make for you here. And it's because I said in the video last few times that horizontal asymptotes, though are approached as x gets to infinity, can be crossed. And what I'm going to do is I'm going to do just, this has nothing to do with the given equation except for the asymptote layout. You could have a graph that looks like this, right? Here's one side, boom, it's following all the rules. Here's the other side, not touching, boom. But you could have a graph that then crosses through in the middle. And you might be thinking, well, how is that allowed? Because the definition of a horizontal asymptote is that it approaches it as x goes to positive and negative infinity. This is just an x value in the middle of, well, your graph, right? It's not as my graph is approaching positive and negative infinity on my x-axis. So you are allowed to cross your horizontal asymptote in scenarios like that. Now, that's not what this graph looks like, but I just wanted to make note of that for you. So let me just clear that. Okay, so now what does this graph look like? Well, what's our x-intercepts? Well, remember, x-intercepts occur when our numerator is 0, and that's never going to happen. So we have none, and we have none. And then what are our y-intercepts? Our y-intercepts occur when x is 0. So when x is 0, we're left with 2 over negative 2, which is negative 1. So we have a y-intercept at negative 1. So you can see, given that negative 1 point, it's possible that our graph is going to go through that middle horizontal asymptote. So we just need to test the behavior as we approach that way and we approach that way. And from the notes, you'll see that I've tried different values. I've tried negative 0.9 for my x because that's approaching my vertical asymptote from one side. And then I've also tried negative 1.1. So the negative 1.1 approaches this asymptote from here, and the negative 0.9 approaches it from that side. And what I get from behavior there is I get this behavior. This line is actually going to shoot down. And again, it's in the notes. And then on the other side, it's going to come down from there. Okay. And then this side will actually turn and go through there. We know it's not going to go through our our horizontal asymptote there because it can't, because now we are eventually going to be moving towards negative infinity. And then the other values I chose to try in the table were 1.9 and 2.1. And what those do is that approaches this asymptote from that side and from that side. And what you get is, in this scenario, you actually get this graph turns back on itself and goes back down again. So like I said, it's possible that it would have turned and gone up and cut through that horizontal asymptote, but it does not in this scenario. And then I also tried negative 10 and positive 10, just to show that my y values start to get infinitely close to 0. So they're both approaching 0, but from the positive, which is why I also have my other half of the graph on that side of my x-axis. So that is my last graph. They're all demonstrated nicely in your notes. And these are only rough sketches. When you get to calculus, you actually start to learn a few other tricks and tools in order to graph more complex polynomials, generally ones with multiple curves, and we figure out where max and min points are. For instance, this is the max of this because it's the peak of that graph. So a lot of these things will sort of come back and bug you once again. So there we go. That's the end of chapter 4. We are going to move into logarithms and exponentials next. Always a joy. I love it so much. Thank you for watching, and I will see you next time.